Hello everyone, welcome to this next set of videos where we will be concentrating on the topic group theory. So this video will cover what is meant by a binary operation along with a non-empty set and the properties that can be satisfied by this non-empty set and the binary property, what is meant by group, and furthermore how this group theory can be developed by adding elements to it. Now we will move on into the concept. Let us consider a non-empty set G with a binary operation called a star, and let any A, B, C be elements that belong to this non-empty set. Then we say that the closure law is going to hold true if for any element A and B that belong to G, if I do the binary operation, that element again has to belong to G. Say suppose I am considering this G to be the non-empty set of integers. So what do you mean by integers? It is the set Z that consists of 0 plus or minus 1 plus or minus 2 and so on. I pick two elements from this A and B from over here. Say suppose I take 2 and I take a minus 5. Now I'll keep this to be the non-empty set and let the operation star defined over here, the binary operation, be the action of addition. So if I am taking addition as the binary operation, the first element, this is the second element, I do the binary operation which is going to be our addition. What happens to 2 plus minus 5? It leads us to minus 3. Does minus 3 belong to the set of integers? Yes. So we can say that the closure law is going to be true over here. Next comes the associative law. Given three elements, if you are going to change the bracket or the order of operation and the value still remains to be the same, that is A star B star C is the same as A star B star C, then you say associative law is going to be true. If I am going to take the same set of integers and I am going to take the binary operation of multiplication and I pick three elements from over here, say I have 3, I have 5 and I have minus 1, and I do the binary operation 3 into 5 into minus 1, so it is 3 into minus 5 and minus 5 into 3 makes it as minus 15. And this I try the other way round, where I first do the operation of 3 into 5 and then go with the multiplication of minus 1. So this makes it as 5 3s are 15 with that of minus 1, which again lands up to be the same 15. So I do now say that the associative law, that is A star B star C, is going to be the same as A star B star C. Next comes the existence of identity element. So what we mean by an identity element is, for any element that you pick from the non-empty set, we will be able to find an element E in such a way that A star E is the same as E star A will give us back our A. So when we look the element, it's just like a mirror. It reflects back the same element. So the mirror over here is called by the name identity element. Consider the set of addition, and if the binary operation is going to be addition, I take any element, say 8, and do the binary operation with a particular element, I'll have to get back the same element called as A. You do the binary operation, the element is going to be written back as the same. So which element is going to do this action? The element called as 0 can perform this action. So with respect to addition, 0 is considered as an identity element. Now consider the binary operation of multiplication. Say suppose you have an element called as minus 5. You do the multiplication and you have an element that returns back the same element, that is minus 5, back to you again. Which element can you think that can perform this action? Yes, you are right. The element 1 can do this action, like when we multiply any element by 1, it returns back to us the same element. An element of such kind will be referred as identity element. Next comes the existence of inverse. What do we mean by inverse? For every element A belonging to G, there is going to be an element denoted by A with a -1 called as A inverse or read as A inverse, which satisfies the property that A star A inverse and inverse of A into A gives us the identity element E. So it is the reflection back to one element to its inverse must give us the mirror. So this is going to be our inverse. So when I take the operation of addition, 2 with respect to some element must give me back the identity element. And what is the identity element with respect to addition? It has to be 0. So for 2, which can be called as an inverse? Yes, we know that -2 can give you back the same number, and in which case the inverse of 2 will be -2. If I am going to take -8 or -8, then -8 plus some element over here has to give me back 0, the identity element. Which element can do this? Yes, the element 8 can do this. So the inverse of the element -8 will be referred as 8. So for every element over here, if a inverse exists, then you call this element A inverse to be the inverse element of the element A. Next comes commutative law. Commutative law is going to be something identical with associative, but not with 3 elements, but we have 2 elements. Over here in associative law, we flip the brackets, but in commutative law, we flip the elements themselves. That is, make your elements go in an upside down way, ulta pulta way, and you get back the same quantity, like A star B is the same as B star A. Then you call the law to be commutative. Say suppose you have an element called as -3 and you have an element called as 2. What will be -3 into 2? That gives us -6. And what do you think is going to be 2 into -3? It's going to be the same -6. So what can we say? The operation, which is going to be multiplication, is going to be commutative in nature. So this is what we say is going to be a commutative law when this holds true. A star B is the same as B star A. Idempotent law. Whenever we have A star A to be A itself, then you call A to be the idempotent element. I know that 0 plus 0 gives me back a 0. A 1 into 1 is giving me back a 1. So what is going to be the idempotent element with respect to addition over here? 0 will be the idempotent element. What will be the element with respect to multiplication? The idempotent element will be the element 1 itself. So this are the few concepts which is now going to build a very important concept called as group. So we quickly recollect that we have seen something called as closure law. Take 2 elements, do the binary operation, then the answer will again be a element in your non-empty set. Do the operation of flipping your brackets, then the elements again belong to the same value. You have an element E that is going to act as a mirror and reflect back the same element which you take. For every element over here, you will be able to find an inverse so that you get the mirror back again. And if you are going to flip your elements and the value remains to be the same, you call it to be a commutative law. An element binary operated with itself, if it is going to give the same element, then you call it as idempotent law. Now comes a word called as semigroup. So what is meant by the definition of semigroup? Let G be the non-empty set with the binary operation star and then we call this G with respect to star as a semi-group if it satisfies the closure law and the associative law. If these two quantities are going to be true alone, that is A comma B belonging to G implies A star B belongs to G, and if I have A star B star C to be the same as A star B star C, then if these two things are true, then you call such a non-empty set with the binary operation as a semi-group. Next comes a monoid. What is a monoid? A non-empty set with a binary operation that satisfies closure, associative and existence of identity, the first three quantity. Or in other way around, I know that a semi-group is something which has closure and associative law. In addition to it, you do a topping of identity element to it, then you call it by the name called as monoid. Now next comes the word called as group. What is meant by a group? A binary operation star with a defined on a non-empty set G that has closure law to be true, associative law true, existence of identity true and inverse true is going to be called as a group. So you have that a monoid has the first three quantities and do a topping of inverse to it, and then the resultant will be called by the name called as group. Now next comes abelian group. What do we mean by abelian group? Let G be a non-empty set with the binary operation star, and if it is going to satisfy closure, associative, identity's existence, inverse existence plus the commutative law, then you call it as abelian group. So a group which is going to be commutative in nature is called as an abelian group. So in this way we start building up the theory from a semi-group and then to a monoid, and then monoid becomes a group, and then a group moves to form an abelian group. So this is how we see that the properties are getting added up to make or build a particular property, which we will be applying it to non-empty sets to test for their existence. I hope this introductory video on the concepts of semi-group, monoid group and abelian group has made us clear the laws that hold true for them and how they can be applied for. Happy learning, keep learning.